Okay, so last time we started talking about titration, and so let's just review what that was all about. We said that in a titration, what you do is you gradually add one reactant into another. Okay, and so the reactant that you gradually add is called the titrant. Okay, it would be placed in a piece of glassware called a burette, and then you add it to the other reactant, which will be in a flask. Okay, and until you add it just enough until you get to what's called the equivalence point. And at the equivalence point, we say that the mole-to-mole ratio of the reactants would be equal to the ratio of their coefficients in the balance equation. Okay, and um, the this, one of these two reactants are, you know very well accurately the amount of one of these two reactants to begin with, and so the goal is to determine the amount of the unknown reactant, the other reactant, which you would call the analyte. The known reactant, that means the reactant with a known concentration, is called the standard. Typically, we said that the titrant is the standard. Okay, although in the case of sodium hydroxide, in the reaction of sodium hydroxide with acids, it's typically the standard, but before we could actually use it as a standard, we compare it against another standard, which we would be placing in a flask. Okay, so let me illustrate that. This is animation that I linked to an animation that I posted on the Moodle site, um, on the free Moodle site. Let me just show you that. So if you go to the Moodle course site, if you look under Internet Resources for Solution Stoichiometry, oops, wrong one. Solution Stoichiometry, Internet Resources. Down here at the bottom, there's a link to a titration simulator. So if you click on that link, it will bring up a Java program. So this is what you'll see. So once it's loaded, you'll get a warning about Java security. Just let it run. And then when you start it, you get something that looks like this. Okay. I have one going already. So this is your burette right here, and you can control the rate at which you're dropping your titrant here. Now in real life, you'd be controlling it by turning this knob right here. Okay, this is called the stopcock. So you turn that to drop the titrant into your flask, and you'll notice there's a thing that's rotating down there. That's called a magnetic stirrer. Okay. So this would be sitting on top of, oops, what did I just do? This would be sitting on top of uh, uh, what did I just do? Okay, this is going to be sitting on top of something that has a steering magnet, rotating magnet at the bottom, and there's a bar there that's will rotate. Okay, so to stir it, although you can just swirl it with your hands if you don't have a magnetic stirrer. And so what you do is, in this simulation, you just click on this stopcock if you want to add the titrant to your flask. Okay, so in this simulation, you can pick your acid, you can pick your sodium hydroxide, and then, like I said, during a titration, close to the equivalence point, something, a drastic observable change occurs that's easily noticed, and so you'll know you are at close to your equivalence point or at the equivalence point. So the point where that happens is called the end point of that titration. So if I did this, I'm dropping my sodium hydroxide to my hydrochloric acid. Okay, and you can be monitoring what's called the pH here. So, and what we've done is we added something called an indicator, phenolphthalein, to this solution in the flask. And what happens is, at the end point of that titration, that is going to turn pink. So if you, And that is because of the, right there, I just stopped the titration. That is because of the rapid change in pH. Just one extra drop around the end point, around the equivalence point, will cause a rapid rise in what's called the pH of the solution, and it's going to cause some what we added here, called phenolphthalein, to turn pink. Okay, so in this particular titration, you added 12.5 milliliters of your titrant, so that's 12.5 milliliters. Okay, and so you have your sodium hydroxide here, and the concentration was 0.2 molar, and you have your hydrochloric acid down here, which is 0.1 molar hydrochloric acid. So that's what a titration looks like. Okay, so let's solve the problem that we talked about earlier. Let's go back to that question. Uh, Here you have a solution. This is what you would do first to determine the precise concentration of a sodium hydroxide solution. A sodium hydroxide solution, as I mentioned, is not something you can readily determine its concentration by simply using the amount of solid and that you use to make the solution. And the reason for that is it's easily contaminated by air. So once you make your sodium hydroxide solid, so once you make your sodium hydroxide solution, you have to compare it against a standard, and our standard in this case is KHP. Okay, so your KHP is KHC8H4O4, potassium acid phthalate. Right, so the name of the compound is potassium hydrogen phthalate. So the P here, PHTHALATE, phthalate. Oops. Yeah. So that P stands for phthalate. Okay. So the reaction, this is what you would call a primary standard. It's something that can be obtained in highly pure form, and it's not readily contaminated. So you compare sodium hydroxide against that. You titrate it against KHP. And the molar mass of this is 204.23 grams. If you figure out the molar mass, you'll find that that's 204.23 grams per mole. So once you've determined you've got sodium hydroxide solution, then you can use your sodium hydroxide to titrate other acids. So let's go back to that example we started last time and solve that problem for the standardization. So let's say you have a titration where you have 2 grams of KHP. Okay, and then to that you added your sodium hydroxide as your titrant. And let's say you used 15 mils of your titrant to reach the equivalent, the endpoint, and we'll take our endpoint as our equivalence point. The question is, what's the molarity of the sodium hydroxide solution? So the reaction here is sodium hydroxide plus KHP gives you water. Okay, so your hydroxide and your H from hydrogen phthalate will give you water plus NaKP, right? Or the net ionic equation would be hydroxide plus the biphthalate ion gives you water plus phthalate ion with a -2 charge. Okay, so you can use either the full molecular equation or the net ionic equation. But the idea here in this particular reaction that the mole-to-mole ratio is 1:1. Okay, 1 mole of sodium hydroxide will be needed to neutralize 1 mole of KHP. So the idea in standardization is this. You're going to know precisely how much KHP you're going to use. You're going to put it on a balance, so you'll get the mass of your KHP. So from the mass of the KHP, you can figure out the moles of KHP. Okay, how do you go from mass to moles, from grams to moles? You're going to need the molar mass of KHP, which is 204.23 grams. And then from the moles of the KHP, you know that the KHP to sodium hydroxide ratio, the mole-to-mole ratio is 1:1. That will allow you to figure out the moles of sodium hydroxide. Okay? And then from the moles of the sodium hydroxide, you divide that by the volume of titrant used. Your titrant is your sodium hydroxide, divided by the volume in liters. That will give you the molarity of sodium hydroxide. So our goal in this experiment then, in this titration, is to determine the molarity of sodium hydroxide accurately, precisely. So this is that's why it's called a standardization titration. So let's do that. Let's start with the mass of our KHP. Which is 2.00 grams. We change that to moles. How do you change moles to grams? Grams to moles. 1 mole of KHP has a mass of 204.23 grams. Okay, so that's KHP. Grams cancel out. Once you figure out moles KHP, then you know how many moles of sodium hydroxide is going to be needed to neutralize it, because the mole-to-mole ratio is 1:1. So you multiply that by 1 mole of sodium hydroxide per mole of KHP. Oops. And so moles KHP cancels out. Now that you know your moles of sodium hydroxide, all you have to do is divide the whole thing by the volume of sodium hydroxide. That will give you your molarity. So let's calculate this one, 2.000. Let me see. What would I put that here? 2 divided by 204.23. And that gives me 0.009793, 4 significant digits. Okay, 009793. That's the moles of sodium hydroxide. And now that you know the moles of sodium hydroxide, you can simply divide that by the volume of the sodium hydroxide that was used to reach the endpoint, which in this case is 15 milliliters. So molarity of sodium hydroxide is moles over liters. So 0.007973 moles divided by the volume in liters is 15.00. Milliliters means 10 to the negative 3 liters. So instead of writing milliliters, I write times 10 to the negative 3. Okay? And of course, this is just 0.01500 liters. So now that I have that, I get the molarity of my sodium hydroxide, which is going to be equal to, let's see, 0.007973 divided by 0.0015, and that would be I think I'm off by 1 0, huh? Oh, I need an extra 0 over here. 0.000. So that's 0.0007973 divided by 0.015. Am I right on this one? Wait a minute. No, I just need 2 zeros. Try it again. 0.007973 divided by 0.015. That gives me 0.5315. Okay. So if I have a bottle of sodium hydroxide that I just made, I'm going to standardize it against KHP, and if this is the result I get, I'm going to put on the label of my bottle sodium hydroxide 0.5315 molar. And then I'm going to put the date that I made it, March 26, and my initial. Okay? So that's my sodium hydroxide solution. Now that I have standardized my sodium hydroxide, I know precisely what its molarity is. I can use it to determine the amount of acid in a sample. So for example, let's say you have a standard solution of sodium hydroxide which has a molarity of 0.4981. Okay, this is molar. And okay, suppose you have a solution like that in the lab, and you use that to determine the amount of HCl in a sample. Okay, so how much HCl is in the sample if 15 mL of solution is required to reach the endpoint? Well, then you're going to have to look at the reaction. HCl plus sodium hydroxide gives you sodium chloride plus H2O. Okay, so you can see from this balance equation, the mole to mole ratio is 1:1. So that means what I need to do then is I'm going to say, okay, I need to calculate moles of sodium hydroxide. So the strategy here is you figure out the moles of your titrant, which is sodium hydroxide. From the moles of sodium hydroxide, you know that it's 1:1. That gives you moles of HCl. Okay. So the question is, how do I know moles of sodium hydroxide? Well, moles of sodium hydroxide is just molarity, moles is just molarity times volume of your titrant, which is in this case is sodium hydroxide. So what's my sodium hydroxide here? 0.4981. Okay, so moles of sodium hydroxide according to this would be, okay, 0.4981 moles per liter. So moles sodium hydroxide, okay, molarity 0.4981 moles per liter times the volume that I used, which is 15.00 times 10 to the negative 3 liters. So liters cancels out. That gives me, that will give me 0.4981 times 0.015 is 0.007415. 0.00747. 00747. Okay, moles of sodium hydroxide. And since the question is how much HCl is there, I know it's a 1:1 ratio. So then I know, then I just change that to moles HCl. So moles sodium hydroxide times 1 mole HCl over 1 mole of sodium hydroxide would give me moles of HCl. It should be the same amount. Okay. So this is going to be 0.007472 moles of HCl. Okay? So that is stoichiometry. Let me just go back to the previous one. I think I may have made an error in my decimal place here. Do I have this number right? Yeah. 979.7973. Yeah. 2 divided by 204.23 is 9793. Okay. Yeah, so I had this one messed up. This should be 9793. Okay, so this should be 9793. Okay, so 0.009793 divided by 0.015, that gives me, okay, 0.6528. 0.009793 divided by 0.015 is 0.6528. Okay, so I got this one wrong. 0.6528 moles per liter. Okay, let's try one from the simulation. and let's see what we get there. Let's do a simulation here. So if you if you click on the chart here, it's going to clear your data. And let's try some other acid. Let's say cyanic acid and sodium hydroxide. Acetic acid, let's do acetic acid and sodium hydroxide. And I'm going to set to 0 my burette. I'm going to fill it near the 0 mark. Okay. Now, it's not always easy to get it to the 0 reading, so you can, as long as you know what the initial reading is, so make sure when you're doing your titration, you take the difference between the initial and final reading. So my initial reading right now is 0 mils. Okay, so I'm going to let it drain until I get to my end point. So my burette has my base, my acid's down here. So let me go ahead and do this titration. Click on this. And I'm going to stop it as soon as it turns pink. And I'm going to see a rapid rise in the pH, and my indicator is going to turn pink when I reach the end point. There, okay, 12.6 milliliters. Now, normally, so it was from 0 to 12.6, and now this is at 12.6. So this difference right here is 12.6 milliliters. Now, ordinarily, if you use a burette in the lab, you should really be able to go to the second decimal place as far as volume in milliliters is concerned. So let's write this as 12.60 milliliters. Okay, and your molarity of your sodium hydroxide is 0.2, and the molarity of your acetic acid is 0.1. So what kind of information can we get from here? So let's go back to this one. So we have acetic acid, which is HC2H3O2 plus sodium hydroxide gives us sodium acetate, NaC2H3O2 plus water. Okay. Again, this is a 1:1 ratio. If you balance this equation, you get a 1:1 ratio. And according to our titration, we used for this, how much did we use? 12.6 milliliters. And this is 0.2 molar. Normally, you should know this to more sig figs than that. So let's just say it's 4 sig figs, okay? So 0.2 molar, 12.6 milliliters. And then this one, you have 0.1 molar. The question is, how many moles did we have here? Okay. So in this particular case, you can say then molarity times volume of sodium hydroxide would give you moles. Okay, so moles of sodium hydroxide is molarity, which is 0.2000 moles per liter, times the volume, which is 12.60 times 10 to the negative 3 liters. So 0.2 times 0.0126 is 0.00252. 2520 moles. Okay? That's moles of sodium hydroxide. So moles of acetic acid then would be what? Moles acetic acid would be the same amount, 0.002520 moles sodium hydroxide times 1 mole of acid per mole of sodium hydroxide. Where did I get this 1:1? From the balance equation. 1 mole of acetic acid would require 1 mole of sodium hydroxide. And so mole sodium hydroxide cancels. That gives you the same moles of acid. So 0.002520 moles acid. So what kind of question might you be asked besides moles of acetic acid in this problem? You could be asked, okay, you were told that in this titration, the molarity of the acetic acid is 0.1. So what's the volume of the acetic acid that was in the flask to begin with? So how much acetic acid was in the flask to begin with? Then you're going to say, all right, so molarity of the acid times the volume of the acid is moles of the acid, right? Molarity times volume equals moles. So if I have, in this particular instance, I figured out the moles of acid, okay? And I'm given the molarity of the acid, so I can figure out what's the volume of the acid that was in there to begin with. So volume of the acid equals moles of acid divided by molarity of the acid, which in this case would be 0.002520 moles divided by the molarity, which is 0.1000 moles. Let's just assume it has 4 sig figs. Okay. So that's going to be equal to 0.02520 liters. In milliliters, that would be 25.20 milliliters. Okay? So that's what you'll need to do. Now, keep in mind that when doing these problems, you really need to know what the balance equation is for the reaction, and you need to know what the mole-to-mole ratio is. So far, we've been doing just cases where the mole-to-mole ratio is 1:1. But in some instances, for example, if you have something like sulfuric acid plus sodium hydroxide, okay, in one of the experiments I posted for the lab, you're going to need, you'll have a 2:1 ratio. Your sodium hydroxide will be in a 2:1 ratio with your sulfuric acid to give you water, okay, plus sodium sulfate. So you do need to know what the balance equation is for your reaction. Okay. Now, titration is not limited to acids. It could, as long as you know what the reaction is, and there's a way for you to determine the equivalence point. So the point in the titration where the mole-to-mole ratio corresponds to that in the balance equation. If there's something you can do to make that equivalence point stand out, suddenly occur with just one drop of titrant, extra titrant, one drop of titrant near the equivalence point, then you'll be able to use titration to determine unknown amounts in the lab. Okay? So that's solution stoichiometry. And so we're going to move on now to gases. Let me stop this recording.